Okay, hello everyone. I'm Bhatta from Storybook University, and I'm very happy to be here to present our recent work on energy dependence of initial conditions from isobar. And this is a preprint number on which you can find all the details of this study. So, as you heard from the previous talk, that the nuclear deformations are generally parameterized by this beta and gamma parameters, which are the quadratic deformation, the parameter beta and the triaxility parameter gamma in the Woods action formalism. And we know that the beta parameter is extracted from the low energy spectroscopic methods. And also we have observed definitive evidence of the impact of deformation parameters on final state observables in heavy ion collisions at both RIC and at LHC. So the question is that a question that we ask is that does the nuclear deformation change with energy scales? And there has been some indication that the description is quite consistent, as has been shown in this particular Atlas paper. And in this particular paper, what we have done is taken the predictions from the low energy predictions regarding the triaxility parameter. And we have studied the impact of the triaxility on the ρ2 ratio, which is the ρ2 is just the covariance between final state flow and mean PT correlations. And we observe that the data supports a triaxial parameter of gamma equals to 30 degrees. So this description is quite consistent.
But based on the what I mentioned, you probably cannot distinguish between
soft and
soft.
Correct. We cannot. So at that point, we just said that it is triaxial, but as you remember from the previous talk, we just found out that we cannot say if the xenon nucleus is a rigid triaxial or a soft triaxial by just using this particular comparison. So to answer this question in more details, we simply take ion collisions at 200 GeV and 5 TeV for ruthenium-ruthenium and zirconium-zirconium isobar collision systems to study the effect of deformation across this large energy scale. So the goal of this study, as I just said, is to check the consistency of the effect of nuclear deformation between 200 GeV and 5 TeV using isobar collisions. And we use a AMPT model, which is based on a transport framework, and it acts as a good proxy for hydro simulation. And we considered these 5 different cases for comparison between the 200 GeV and 5 TeV. These 5 cases have different values of deformation parameters as well as these Woods action parameters. And before we go to the comparison, we note that at two energies, at 200 GeV and 5 TeV, the in-charge distribution looks very different. The values are very different. So to compare them, what we do is we take the 1% of the distribution at both these energies, and we scale the 5 TeV distribution to match the 1% of the 200 GeV distribution, so that it looks like this. And we using this scaled in-charge, we compare this the observables of these two energies. So part 1 of my talk is to study the impact of fluctuations on flow ratios in isobar collisions, and this is before we actually go into studying the effect of deformations at these two different energies. So as we know, the final state elliptic flow V2 it emerges as a response to initial state eccentricity, and it is driven by pressure gradients. And we also know that V2 is proportional to epsilon 2, even in very central collisions. But we see that even in very central collisions, there is a spread to this particular proportionality that we are showing here. And so this particular proportionality is only true on an average. But in reality, what we observe is that V2 can be, the two particle V2 can be decomposed into 2 distinct parts. One part is the flow which originates as a response to the initial state participant geometry, which is called V2PP, and the second part is called is the part of the flow that is uncorrelated to participant geometry. So in this particular decomposition, please note that delta 2 also contains all the non-flow and short-range correlation that we generally measure in the final state flows. So the question here we ask is that what is the origin of this delta 2, what is the nature of delta 2, and what is the impact of this delta 2 on isobar flow ratios. And what we do to answer these questions is we probe the variation of delta 2 by varying nuclear structure parameters using isobar collisions as a handle. And we also check the response of delta to Wood section parameters at different center of mass energies. So in this first plot, I'm showing the V2, the two particle flow ratio as a function of n charge. And these ratios are between these 5 different cases. And in this particular workshop, as we have seen in the talks by Giuliano, Professor Gia, and Chunjan, we have seen that increasing the beta 2 parameter leads to increasing the V2 in the central collisions. Increasing beta 3 parameter increases V2 in the mid-central collisions, increasing A0 and decreases V2 in mid-central events, and again, R0 has a small effect on V2 in mid-central events. And this has been extensively discussed in a lot of previous talks. But what we observe in this particular plot is that if you compare between these ratios at RIC and LHC, the ratios have a very good qualitative agreement between these two energies. But we also note that the ratios at LHC, which is shown here in the solid lines, have a stronger response on V2 at this LHC. So the deformations have stronger response to flow at LHC than at RIC. Next, when you try to understand the impact of delta 2 on the V2 ratios, again, we go back to the same decomposition. The first plot here shows the ratio of the impact of deformation parameters on the two particle flow. The second plot shows the impact of deformation again on the V2PP, that is the flow which originates as a response to the initial state participant geometry. And the third plot shows the impact of, again, all these Wood section parameters on the delta 2, which is the part which is uncorrelated to the geometry. As you can see here, the magnitude of the ratios for the V2PP is in general larger than the magnitude of the ratio of V2 two particle flow. And second, we also observe that the ratio of delta 2 at both energies is almost very close to 1 for all these, for the variation of all these different Wood section parameters. So what you can observe from this particular slide is that delta 2 dilutes the impact of initial state participant geometry on final state V2. Similarly, if you look at the three particle, the third harmonic flow, we also again have the same observation that delta 3 dilutes the impact of the V3 PP on the final state V3, which you get from the two particle correlations. So the conclusion from this particular part of my talk is that delta 2, 3 are not influenced by changing the overall deformation in the initial state geometry, even with changing center of mass energies. So what we think is that delta 2, 3 might originate from fluctuations in initial state, which are of small scale, that is smaller than the global geometry, for example, subnucleonic fluctuations, or from the stochastic effects from higher state evolution of the system. But this is just what we think might be happening. But what we observed in this particular study is that delta 2, 3 dilutes the effect of nuclear geometry on final state flow estimates. Coming to the part 2 of my talk is so in this part we study the response of flow estimates to the deformation with varying center of mass energies. So before we go on to measuring these different flow estimates, again we go back to our same decomposition, and in which we note that V2PP is a response to the initial state participant geometry, and we could think that the initial state initial eccentricity could be decomposed into various independent components. These components might arise from fluctuations, from the average geometry, average collision geometry, as well as from deformations. And as shown here, and this all the three components can be viewed from these two figures which are shown here, where the reaction plane geometry, which is the average geometry, responds to this collision geometry, and the E2PP corresponds to the geometry defined by the participants inside this average geometry. And as we have also seen in previous talks and previous papers that we also have components from deformation contributing to the initial state eccentricity. Again, we know that V2 arises as a response to the initial state eccentricity, and so if you just take this particular decomposition, And we assume that each of these components have their independent response coefficients that transfers this initial eccentricity to final state, that transfers the contribution from the initial state eccentricity to final state flow. We could define the flow coming from this fluctuation part with a response coefficient of kappa 0, the flow originating from average geometry with a kappa RP. And likewise, for the different deformations, we could also define the flow which originates from the as a response to the eccentricities created by these deformations. Of all these different terms that go into the final state flow, this particular term is the reaction plane flow. This particular term is the flow from beta 2, and this particular term is the flow from beta 3. And these 4 different terms constitute what is the V2PP in our initial decomposition. So now if we compare between the different flow estimates, and also we have included the delta 2 in this particular plot. So this plot shows the different estimates of V2 as a function of scaled N charge for ruthenium-lithium collisions for 2 different energies. And what we observe is that the result for LHC, which is shown here in the solid lines, are in general larger than the V2 observed at Rick. But that we know that is expected because of more frequent Parkman scattering. But what we also observe is that the 2-particle flow is larger than PP, the participant plane flow, which is again larger than the reaction plane flow. And we also did expect that, and we observed that at both energies. But what is interesting to note in this particular plot is that delta 2, which is shown here in the solid blue line at LHC, is actually very close to the flow originating from the participant plane geometry. So in a way, we could say that the contribution to final state flow from sources uncorrelated to the initial geometry is as large as those arising from initial state geometry itself. So that is something that is interesting from this particular study. Going on to the contribution of the initial state eccentricities arising from deformations and how it impacts the final state flow. The plot on the left top shows the eccentricity from beta 2 and epsilon 2, the second harmonic eccentricity from beta 3 at 2 different energies again. And as you can see from this particular comparison, the eccentricities coming from deformations at the 2 different energies are actually very close to each other as a function of N charge. But if you look at the V2, the flow which originates as a response to this eccentricity are actually very different at 2 different energies. And we also again observe that deformations lead to a larger flow at LHC than at RIC for both these components. So naturally, we ask the question, how does this K2 for different flow components evolve with center of mass energy? So to study that, we define our response coefficients as just V2 over epsilon 2 from beta 2, V2 from over epsilon 2 over beta 3, and for third harmonic, we also define a similar term. And as you can expect, the K2 from beta 2 is expected to be larger than K2 of beta 2. It is expected to be larger for LHC than what we observe at RIC, because epsilon 2 is almost from beta 2 is almost same at both energies. And if you and these are the response coefficients that we study: the response coefficient to initial state eccentricity from participant geometry, the response coefficients for average geometry, and the response coefficient for eccentricities originating from deformation. And this is the result that we get as a function of N charge. And this plot shows the ratio of response coefficients at LHC over RIC as a function of N charge. And I've just listed a few observations, and that this is what we just observed from this particular plot. We observed that the magnitude of this response coefficient from between LHC and RIC is greater than 1. So this is also what leads to a larger flow at LHC over LHC than what we observe at RIC. But what we also observe is that the response coefficient, the evolution of response coefficients to the initial state average geometry is actually very small in central events, whereas the response coefficients for participant geometry is largest in the mid-central. The ratio is largest in the mid-central. Another interesting observation from this particular plot is that the ratio of the response coefficients to participant geometry from LHC and RIG between LHC and RIG is almost same as what we get from the response coefficients for eccentricities from beta 2. So what we observe from this particular result is that the difference in evolution of response coefficients between these two energies leads to a major difference in observed flow coefficients in response to the same geometry. Finally, I also saw the result of the N charge ratio as a function of N charge, and this has again been shown extensively in the previous talks. But the interesting thing to note here is that the effect of the changing Wood section parameters between 200 kV and 5 kV are very consistent. That is, the P-N charge is actually robust observable to study the effect of nuclear deformation, irrespective of center of mass energy. So in conclusion, we have tried to answer that does nuclear deformation manifest itself in the same way across the energy scales? And we observed that at both the center of mass energies, this delta 2-3 component actually dilutes the effect of nuclear geometry towards final state flow estimates. And we also observed that even for the same nuclear structure, the K2 ratio, the response coefficient ratio between LHC and RIG is greater than 1, which results in a larger flow at LHC than at RIG. We also observed that the P-N charge is a robust observable to study the effect of deformation, irrespective of center of mass energy. And in the future scope of this study is to study the same thing, to carry out a similar study with a model with saturation effects, so that we can disentangle the effect of saturation and deformation towards eccentricities in initial state and flow in final state. Thank you.
Yes.
Yeah, so going back to what you're talking about with the fuzz around the B2 to epsilon 2 ratio, you don't have to go back to the slide, but you were saying that this is something that can be from non-flow effect or other effects, but I would really caution you away from that interpretation, because what you're showing there are just theory model to theory model. And so really what you have is you have an expansion, right? So that you're just using the leading order term of your expansion.
Yes.
But you can have other eccentricities that actually contribute to this. So it's not that they're non-flow, it's just that there's other geometrical effects that could be giving you these results. So you can get like contributions to B2 that are not just from epsilon 2. They can be mixed terms that are like second order eccentricities.
So in a way, you were saying that these terms might not be exactly independent of each other.
No, absolutely not. So
right.
we have, I mean, if you go to my talk yesterday, and we have a few papers on this, where it's just a series and you can expand out in the series.
Okay.
And so to get a more precise mapping, especially for mid-central to peripheral collisions, it's a well-defined quantity where you just add higher order terms to this.
Yeah.
If you go back to your response of the delta or on the deformation, put one any of the plot. I think that okay, go forward. This is a good way to illustrate. Using the nuclear structure actually allow you to probe how these two components respond to the geometry you're imposing the initial condition. It's actually quite interesting that whatever this delta is, this fuzziness, have no knowledge about the global geometry you put in. Okay? You put in deformation, or you put in neutron scan, or you change the radius. You see delta 3 do not respond. This fuzziness do not respond to the global geometry. We can use nuclear structure to probe the response in this model at least, right? So it's actually quite non-trivial to see this, because that means when you do a two-particle measurement, you see isobar ratio. These isobar ratios have a weaker response than what the participant plane eccentricity would tell you, right? Because they really dilute the response, and that dilution actually is energy dependent.
Yeah, absolutely.
Yeah.
So we found also this energy dependence, where you get a better response at LHC than you do at RIG.
Right. And you also see the stronger, even in the participant plane, if you compare the open red and the solid, the line, the LHC have for the same deformation you put in, LHC have a stronger response also, somewhat.
Just on this slide, how did you separate these two contributions?
Okay, so this one is measured from the final state two particle measurement, and this one is V3 pp is just a projection of the final state V3 along the epsilon 3 pp. Go back. Yeah, so For example, here the V22 could be the direction of V22 could be in this direction, and the V2PP would be the projection of this vector along the epsilon 2PP.
So you need to define the reaction plane. Oh,
So this one is again could be calculated from the initial.
so it's essentially epsilon 2,
Oh,
it's
yes.
epsilon 3 pp.
Right, it's I might have the formula. Hopefully. Yes, okay. So VNPP is calculated in just in this way. This is a projection of the finite state Vn along the initial state eccentricity defined by the participants in the initial state.
So you use a part of the initial condition to cancel out on the numerical.
Yes.
Numerical denominator.
Yes.
And use the flow to.
And then you can just calculate this delta n by taking a quadrature, like square root over the differences of the squares, right?